So please look at the current video. We look at an interesting concept which is called similarity among the matrices. And we're assuming that all the matrices we talk about in this video are all square sized and they have the same size n by n. And please look at my notation. A is similar to B. And this fact is defined by actually there exists a matrix P such that we actually have a matrix equation like this. P inverse times A times P is actually B, which means we want an invertible matrix P such that we have such a matrix equation. If I randomly give you two different matrices of the same size and both are square, let's say, it is not an obvious exercise to see whether they are similar or not sometimes, but there are still some properties we can use. So can you see why, under the condition that the two matrices are similar, the determinant of the two matrices must be the same? You can actually prove it yourself because we have such an equation already. So it basically means there exists an invertible matrix P such that we'll have this equation after applying the determinant formula to both ends of the matrix equation here. And please recall the determinant property with regard to matrix multiplication. We can actually split it like this. So it requires you to understand the property of determinant extremely well. Please recall this fact. And you see the fact is if you recall the property of the inverse of a matrix correspond to its determinant, the fact is the determinant of P inverse can be written as 1 over determinant of P. So you see basically it means what? It means I can cancel out these two common factors and it gives us the sense that determinant A must be the same as determinant B, right? And let's look at the second property. But before the second property, please think of it as an invariant in the sense that whenever two matrices are similar, it means the determinant of them must be the same. But the opposite may not be true. The opposite means if I give you two matrices with the same determinant, it does not automatically imply that they are similar. So it only goes one way, but it's still quite a good invariant, right? In the sense that if I give you two matrices, if their determinants are not the same, we can easily say that they are not similar, right? Let me put it here. And you see my notation that A is not similar to B means that you are not able to find such an invertible matrix P to satisfy such a matrix equation blue star. And let's look at further invariants here. So I'm claiming that the characteristic polynomial of the two matrices must be the same if they are similar. And can you prove why it must be true? I can actually start with the right hand side, you see, then I plug in the blue star equation for B. It means I can write it like this, right? And the next part is kind of artificial because you see, for the first matrix, it's quite clear that the identity matrix is 1. It means I can artificially make it up like this. It is still an identity matrix because I'm multiplying P inverse times identity times P, right? So the fact that I'm doing it is that, please recall that the constant is quite flexible, the lambda. I can actually make it like this for the next step. And the reason I'm doing this strange step is that I can take out the P inverse, open bracket, lambda I minus A, close bracket, times matrix P. So please look at all my steps. These are all valid. And the next step, we can use the special determinant property to split the matrix product. Now you see, you actually have three matrices multiplied together. I can split the determinant like this. And also recall that this determinant is basically 1 over determinant of P, right? And once again, as a common factor, these two cancel. It gives you a sense that at the end, it is the same as the determinant of lambda I minus A, right? And that's the reason why the characteristic polynomial of the two matrices are the same. When the two matrices are similar, and once again, the opposite direction is not correct. It means if I give you two matrices with the same characteristic polynomial, it does not automatically imply they are similar. It only goes one way, but nevertheless, it is still quite a useful invariant to use here. Because basically, it means that whenever you're given two matrices, when they don't have the same characteristic polynomial, we directly know that they cannot be similar to each other, right? And let's look at the last property here, but I think the last property is obvious if you understand the characteristic polynomial, because you see, the characteristic polynomial can help us find the eigenvalues, right? Because the eigenvalues are basically the roots by setting this polynomial to be 0. And it basically means because both matrices have the same polynomial in lambda, it means both matrices have the same eigenvalues. But I think that is more obvious when you understand the property 2 already. And once again, if our two matrices have the same set of eigenvalues, it does not automatically imply they are similar. It doesn't, but we can only say that when they don't have the same set of eigenvalues, they cannot be similar to each other. So it means what? It means these three properties actually are quite helpful to prove in certain cases which are slightly more obvious that two matrices are not similar to each other. So let's look at some exercises. So please look at the given two matrices AB in part A. Can you see why they are not similar? So we can use the previous three properties, right? We can look at the determinant first, which is 6 for the first case, and the second case actually has determinant -1. And because they are not the same, by the property 1, we understand that A is not similar to B, right? And let's look at the part B. So can you see why these two matrices are not similar to each other? Let's find the determinant first. For the A, it actually has determinant 1, and determinant B is actually 1. So it means they are the same, right? But it doesn't imply they are similar just because the determinant is the same. And let's look at the second step, which is to find the characteristic polynomial of the two cases. So you see for the first matrix, it has the polynomial as lambda squared minus 3 lambda plus 1. And let's look at the second characteristic polynomial. The second polynomial is lambda squared minus 4 lambda plus 1. It means they are not the same, right? So it automatically implies that by our property 2, the matrix A is not similar to the matrix B. We'll go deeper than that in the future.